All right. Hey class, thanks for tuning in, and in this video, this is part 2 of population ecology. So I would suggest you go back and watch the video titled Exponential and Logistic Growth if you are having a hard time understanding exponential and logistic growth and how to read graphs of population growth. Okay, so in this video, helping you understand how populations change in an ecosystem, we're going to look at some factors that affect population growth. So thinking back to the last video, now again, if you look at this and you go, I don't know what this is, I would say stop here, go back, look in the textbook, or watch the previous video I made called Population and Logistic Growth. Okay, so when we reach a carrying capacity, okay, what are some factors that can affect that carrying capacity and move it up, move it down? So all of these factors we're going to look at are limiting factors. So these are some sort of factor in an environment that puts pressure and resistance on population growth that kind of forces it to go from this shooting exponential growth to flattening out. So, think about, pause the video here. What are some factors that you can think of that could keep a population from growing? You have an aquarium at home, in your backyard, thinking about weeds that might grow, insects that all of a sudden appear. What are some factors that could keep it from growing exponentially forever, that cause it to stop at some point? Pause the video, take a quick moment. Okay, so you thought of some factors. Let's break down factors into two main categories. First, there are density-dependent factors. Okay, so they are factors that depend on the density of a population. Okay, and these factors will change based on how many there are. If you have a really dense population versus a super spread out, sparse population. So some examples are competition. Okay, competition, if you have 2 people in all of Clovis area, there's going to be no competition. But now you try to cram 3 billion people inside of Clovis, there's going to be a ton of competition for food. People are going to be shoving each other and throwing punches in Walmart trying to get the last bag of cheese that's left in the store. Okay, and likewise, as the population increases, you get more dense, more packed in an ecosystem. Competition increases. Okay, disease, the same thing. Okay, the more dense a population, the more likely disease will have a major effect. Okay, because if you have 2 people living in Clovis, the chances of them spreading coronavirus pretty low. But like places like New York City that have a high population density, okay, coronavirus is able to spread more and to cause more death. Have more of a factor on population growth in really dense areas. Okay, also resource availability. Do you have a lot of food in your environment? Okay, that question depends on how many people you have. Now, think about our classroom. Okay, if we had a potluck with just one table with food, one table of cheeseburgers. Okay, if there are only 2 of us in this classroom, that's not going to be a factor. But as more people learn about this cheeseburger buffet and start coming into room 664, all of a sudden that cheeseburger table is going to be more of a factor. Okay, if you cram 100 people in here, the availability of cheeseburgers is going to become a bigger deal as that population goes up. And the same with space. Okay, as your population increases in size, space becomes more and more of a limiting factor. Okay, so these are density-dependent factors. The bigger your population, the more of an influence, the more of an effect they have on keeping your population growth down. Now, the other category factors, they don't care about population density. These factors don't change based off of whether you have just 1 individual or a billion individuals in the same space, and they're called density-independent factors. They are independent of density. And so usually these are natural disasters. You can have a meteor that comes down and hits Clovis East. Doesn't matter if there's 1 pigeon or 1,000,000 pigeons, those pigeons are gone. Okay? The density of the population didn't matter. Okay, and an earthquake happens. Okay, that earthquake's going to equally affect a population of 1, a population of 1,000,000. Okay. Another natural disaster, a flood. Okay, the density of the population doesn't have an effect. The flood's going to knock out population of 1, population of 100, population of 1,000,000. Okay. Also, human activity can be thought of as a density independent factor. You can have habitat change. Let's stick with that one. So you have land use. You have a bulldozer. It comes in. The homes that are being built around Clovis East. When those homes go on top of what once was a grassland habitat, any mammals, any insects, any birds that were living in that habitat, they're gone. It doesn't matter if there was a gopher population of 1,000,000 or one single rabbit living in the grassland. Okay, that habitat from human activity is going to level the population and remove it. You can also think of pesticide and herbicide application. So when farmers, they want to get rid of all the weeds, it doesn't matter if there's one weed or thousands of a weed, that pesticide is going to kill 99% of them, okay? The density doesn't matter. Its effectiveness will be the same. So density independent, doesn't matter how dense the population is, that factor has the same effect. Okay, now when we're thinking about growth and how the population graph looks will depend on how quickly a population can make babies and how many babies it can make at once. So we call this biotic potential. So in ideal condition, what's the maximum reproduction rate of a population? And that is going to, put populations in two categories. One is R selection. So R selected species, they're boom and bust. They're going to make a ton of babies. They have a high biotic potential, so they're going to reproduce a lot. Boom, tons of babies. A lot of them are going to die. They're going to get eaten. They're not going to be able to get their resources, so a lot of them die. And these populations have a short lifespan. They don't live too long. They grow quickly. They crash quickly. Examples, insects, some fish, some small mammals, okay? It's kind of like a spray and pray approach. I'm going to make so many babies, I'm hoping a few survive. Another example is case selection, okay? Humans and other mammals are like this. They have a lower biotic potential, okay? They're not going to make a whole lot of babies at once. Okay, you think about humans, it's 1, maybe 2, 3, 8 if it's like a really crazy low probability example. Most times 1, okay, compared to millions for insects. Okay, so not very many babies, but a lot of those a higher percentage of those babies will make it. Okay, the parents are going to take care of them. So with a longer lifespan, there's less rapid growth, but there's usually less population crash too. Okay, so mammals are a big example of case selection. And so R-selected and K-selected growth will look different. So R-selected is going to have a huge boom and bust. It's going to be overshooting that carrying capacity all the time and going way below the carrying capacity all the time. So there's big old fluctuation for R species in the red line. K-selected, different. It has a longer lag phase. Okay, and that exponential growth is not quite as its rate's not as large as R-selected. And when it reaches the carrying capacity, its fluctuations are not as great. Now, this is not on your worksheet, but this type of thinking of R-selected individuals that don't live very long, a lot of them die, but a lot of babies are being made, and so you just have so many babies being made that enough survive to increase the population. Versus case selected, where not as many babies are being made, but more of them are surviving. We can think about the survivorship model on your worksheet, where type 1 and survivorship models is his number of survivors and then time until and time. So at the top left, everyone survives, and then as we go to the right, eventually at some age, all will die. And depending on, and the graph will change depending on how quickly that happens and where that happens. So in type 1, more case selected, okay, the deaths don't happen so quickly. Okay, so not as many newborns are dying, a slower death rate at the beginning, and then at a certain age, that death rate increases, usually like post-reproductive. So a lot more of the organisms in type 1 are making it to reproductive age, and the majority of them are dying at the post-reproductive age. Okay, and we'll jump to type 3. Type 3 is the opposite, where a lot of the babies are dying at the very beginning. Okay, so all those eggs get laid, and they all hatch, and so there are lots of them. Okay, but a lot of them are dying before they reach reproductive age. So when they reach reproductive age, you have very few compared to what you originally did. And so, post-reproductive age, there's not as many deaths, but it's because the vast majority of them have already died. And then you have type 2, where it's in between, where it's all balanced. There's a steady death rate as you go. All right. I hope this video helps you with your population growth worksheet. And again, if you have questions, see me in office hours and message me at any time. Miss you all and hope you're all safe. Bye.